with percent composition, it's a little bit different than the mole ratio, like in our lab of 2 of these for every 3 of those, or 1 of these for every 3 of those. Percent composition is based upon the formula of a compound, how much by mass is each part. So it requires us to still know a little bit from the periodic table dealing with the mass of these compounds. So let's get out a periodic table as well. So in order to do this sheet we picked up on the way in, we are going to have our periodic table, we're going to have a calculator, and the sheet itself. There's actually more math that we could include in this unit. For example, after percent composition, it's very common that teachers would go over something called empirical formula with students. However, we don't have the time to really go into that if we want to be done prior to winter break with this unit. So by teaching you percent composition, if you were to take a future chemistry class, like a college chemistry course or even AP chemistry, we could take you that next step. If you look towards the bottom of your page, again, top half of the page is an explanation of something. The middle part gives how to do it. I'm just going to go over sample problems to show you right now. A percent composition problem, it's very common that we will give you the written name of a compound. And I'm hoping that you guys realize that when you're given the written name of a compound, the first thing you should be doing is trying to write the formula. That's going to hold true for a lot of what we do throughout the year. So why don't you take a little 15 seconds right now for copper 1 oxide to write out the formula. I'm going to do myself now, I'm a guy. Tess, what's the formula? Cu2O. Now, in the lab that we just did, what we would say is that it's a 2-to-1 ratio between the copper and the oxygen. Are we okay with that statement? And there's assumed 1 after the oxygen. So one way to describe what makes up copper 1 oxide is it's a 2-to-1 ratio of copper to oxygen. However, that doesn't take into account that copper is a much larger atom than oxygen is. While you guys were doing this, I was just doing a quick head count here, and heck, let's include if Cole was actually here today. If Cole was here today, we'd have 12 guys in the room and 13 girls in the room. And then let's just say, because I wanted even numbers, I'd kick Alyssa out because she's causing a lot of distraction back there. We have a 12 girls, 12 guy ratio. It would be a 1-to-1 ratio of guys to girls. Does that mean that we'd have the same ratio by mass of guys to girls? Probably not. Again, different individuals have different masses. That's true for people. That's true for the elements as well. So the lab that we just did was trying to break down in a compound what's the ratio of the two things just by how many of them are. Percent composition isn't as worried about how many there is. It's more worried about by mass. So if step number 1 is we need to know the formula of that compound, step number 2 is we need to know the mass of each part. And the reason why I asked you to get out your periodic table is your periodic table. That same number that's used for mole conversions, that's used here as well. So if you look for copper, which should be in the middle of your periodic table, it's that d orbital. I usually go to the hundredths place with this. So what would be the mass of copper, Charlie? 63.55. Now, there are 2 in the formula, so we do take that into account, and we multiply that by 2, which would be 1, 2, and probably a 7 and a 1. Oxygen's 15.9994. Well, that's 16.00. Times 1 because there's 1 of them. So here's our step 2. We need to know the mass of each part. Percent composition not only requires that you know the mass of each part, you need to know the total as well. So we're going to add these 2 together. That's a 0.1, that's a 3, carry the 1, 43.1. Lastly, if we know the total and we know the part, to find the percent of anything, it's part divided by total. So if I take 127.1 divided by 143.1, and I take 16 divided by 143.1, that will give me a decimal value. Remember, decimals, then we can multiply by 100 to express those as a percent. Now, students will ask, how do we round it off? Do we base it off of sig digs, which means I have 4 digits, or is there a certain way you round it off to the ones place? We typically worry about sig digs with measured values, things that you do within the laboratory that you actually measure out. I consider the periodic table, although at some point they had to be measured to get those values, to be more of a known value. So we're a little bit more lenient when it comes to sig digs. So for example, when I did this math, I got 88.8%. I rounded to the tenths place. I'm not doing a ton of digits, I'm not only doing a couple digits. The oxygen then is 11.2%. So the math that we are introducing today, that we'll work on in the lab next class, we'll work on it for the homework, will be on your test. This is it. This is taking that mole conversion numbers from the periodic table and just figuring out by mass what's the percent of each part of the compound. Because the lab we just did was by the number of particles, what is their breakdown. But consider that some elements have a greater percent than others. I want to do one more with you right now, and that's letter B. Letter B is hydrogen gas. What's the formula for hydrogen gas?
Or H2.
H2. Remember, it's one of our diatomics. This is kind of a silly problem, but we're going to do it anyways. If I look on the periodic table, hydrogen is 1.01, and in the formula, there's 2 of them. That gets me a mass of hydrogen of being 2.02. Hydrogen is the only element in hydrogen gas, so I guess 2.02 divided by 2.02. Again, this is silly because I've just mathematically proved that hydrogen gas is made up of 100% hydrogen. Yeah, it's an unusual problem, but I really just wanted to remind you of diatomics. The text on the top, I have a bold word in the first paragraph. That's what a hydrated compound is. At the end of the first paragraph, I give you an example of a hydrated compound. It's those blue crystals that we worked with early in the year. Right here are those blue crystals. What's unique about some ionic compounds is that they actually are more stable when they are around water. Remember we did a lab where we took these white little Dippin' Dots, we left them in the cabinet over the weekend, we came back and they looked all wet? That was calcium chloride. Calcium chloride can exist without water attached to it, but it's more likely to exist with water attached to it. When you see things that look more crystalline in structure, that crystal-likeness of it is probably due to water that's loosely attached to it. So in order for us to accurately talk about the chemicals that we work in class, we can't simplify and omit the water part. Instead, we have to label these chemicals with their full formula. So this is the next, and for you guys, hopefully, thankfully, the last step in naming that we do the entire year. Because again, first semester is all about getting you information, getting you the tools that you need in order to do second semester. If we don't know how to name things, second semester we're in trouble. If we don't know how to do mole conversions, second semester we're in trouble. If we don't know the difference between a polar and a nonpolar molecule, things that we've just covered in this unit, although we wouldn't have been able to know that without learning electronegativity in the last unit. A lot of things carry over second semester. This is us trying to tie one of those last loose ends in order for us to do that. So the first paragraph is just talking about the fact that when you hydrate yourself, you're taking in water. That is a term that people are familiar with. Well, some ionic compounds are hydrates. That means that they have water attached to them. Notice the second paragraph. I give you the formula of those blue crystals. CuSO4.5H2O. And then the third paragraph, I start by saying the dot between the salt, which is the ionic compound, and the water does not mean multiplication. It shows that water is loosely attached to the ionic compound. Remember what we did with these blue crystals in the lab? We heated them up in a test tube. And we heated up in the test tube, the water all evaporated out. Not only that, but then these changed to white crystals when the water evaporated out. So we were breaking that loose bond, in other words, between the two. That's the same sort of stuff that we're going to be doing in the lab next class and next week. Now, also in that third paragraph, there is a second bold term. So again, these are terms that we want you to be aware of. So besides I having them bolded, perhaps you want to underline or make note of that you need to know what a hydrate is. That's an ionic compound that has water molecules attached to it. And you need to know what it means to be anhydrous. Anhydrous means without water, which is what the bottom part says. So again, anhydrous is a compound without water. When we heat this up to the point where all the water evaporated up, it's no longer a hydrated compound because we got rid of the hydrate. We got rid of the water. So it would be called anhydrous. Notice at the bottom of the sheet, we once again have to know how to go from formula to written name or written name to formula. How you would approach this. Nothing has changed prior to the dot. So in these first three problems, I would name those just like I've named them in the past. So if I gave you BaCl2, what would we name that? What's the name for BaCl2? Stack, what would we call Ba? It would be barium chloride. Now, BaCl2 is barium chloride. BaCl2.2H2O has to have a slightly different name. And what I have, well, that's not going to work. What I have further up the sheet, it talks about the fact that to water, we can use the Greek prefix for two to show that there's two waters attached. So Greek prefix is on that polyatomic ion sheet on the bottom Tyler, do you have that sheet in front of you? What's the prefix for 2? Di. If we're not going to call it dye water, we call it dihydrate. So the written name of BaCl2.2H2O is barium chloride dihydrate. Some ionic compounds exist loosely attached to water. We need to indicate that. I want to do the very last question on here with you right now, where if we give you the written name nickel 2 nitrate hexahydrate, you should be able to come up with the written formula. When it says nickel 2, that means I have nickel with a +2 charge. Kinsey, nitrate is a polyatomic ion. What's its formula? NO3. And what's its charge? -1. Whenever you're naming these hydrated compounds, which once again means water is loosely attached to these ionic compounds, I would first just figure out the ionic part. So Brooklyn, I have Ni with a +2, I have NO3 with a -1. What would just be the formula of that? NiNO3 2. NiNO3 2. Then NO3 is in the parentheses, 2 on the outside. But then we see hexahydrate. So we put a dot to represent that loose bond between water. Question or answer? Okay. 6H2O. Hexa is the prefix for 6. Hydrate means water. Just like with the percent comp where we went over a couple of problems and you did a few, why don't you fill in the rest of these right now? We'll give you a minute or two to do that, and then we will go over those answers as well.